This is an underground excavation. So anyone here from the part-time students who is involved in metro? So now what
Yes,
you
sir.
see
Yes,
here.
sir.
Okay, who please call out your names because I'm not able to see your pictures. Who are working in metro?
Sir, Himanshu.
Oh, Himanshu. Okay.
Sir, Akanksha.
Himanshu and Akanksha both are working in metro. So do you do any monitoring over there? Structural health monitoring? Or is it a different department?
No, sir. Not right now, sir.
Okay, so basically now here what you see here is an excavation, and excavation needs to be guarded by vertical panels, and these panels are kept in position by these circular compression members. These are pipes. So there was one accident involving, because these excavations are quite deep, 30-40 meters.
Struts.
Yeah. So there was one accident in Singapore in 2004, Nicol Highway Expressway, where one of these struts, it had buckled out. So when it buckled out, so that led to increase of the forces or stresses in the other adjoining struts also. So eventually it broke down, and it caused sinking of the highway nearby. So these are these should be monitored. So here I am showing you this paper. It's very interesting paper written by Batten, and these are people are sort of pioneers in monitoring the underground excavation. So they have
Sir, is it the Nicol Highway?
no, this is different. They have done monitoring in other parts of Europe. Okay, so they suggest that if we are monitoring a circular section and we are interested in finding the compression forces, they advise that we should instrument at least 3 sensors. At least 3 sensors should be there. Alright, that's what they are advising. Why? Because when we are subjecting a strut to compression, what will happen is that unwanted bending will always be there, because the strut which are very slender, they show a pattern of being drifted on one side on account of the compression forces. That's like the precursor to buckling. So that's why, to eliminate the bending stresses, it's very important that we should have multiple sensors, and they advise that we should have minimum 3 sensors, at least 3 strain gauges. Then we can we can measure the actual force to a reliable degree. So it will be very good to read this paper, because they have done a lot of practical studies with the underground metro. So I'll share this paper, or you can find it yourself. It's available in the open access also, so you all can go through it. And now I want to highlight something. Let me just share now the Word file, the question paper, and then we'll discuss that. And I'll also show where there were the points of the mistake. So question number 1. Mild steel pipe section of 500 mm internal diameter and 10 mm thickness is used to restrain earth retaining vertical panels in an underground excavation for metro construction. At one particular section, 5 vibrating wire strain gauges of this much gauge length, they are instrumented in the longitudinal direction. So the baseline frequency is given for the these 5 sensors. So these details were given. So you were asked that what is the actual force, because we are getting here different values. Some are showing that there is a tension also. So what is the force in the pipe? That's one question. And second is that why these vibrating wire strain gauges, they are showing both tension and compression, while we understand that the pipe should be under compression. So part B reason must be clear now, because whenever we are undergoing subjecting a slender member to compression, there will be some bending because of the tendency to undergo buckling. So that is responsible for this reason, that although the member is under compression, but still some sensors, they are showing tension also. Alright, and part A. So part A, most of you have done this mistake, that you are using only one sensor to calculate the axial force. No, you have to use all, but they are not to be algebraically added. You have to find the average strain. So average strain will be such that it will eliminate the bending effects. Now let's see some of the configurations. Let's see some of the possible configurations, so that will further answer your queries. Some of you have raised queries. So let's say I choose a circular section. I am using pen, a tablet pen, and let me just draw something first. Insert shape. Let me insert some circular shapes. Sorry, this is sorry, I am a little bit stuck. Just give me a minute. Yeah, now it's in control. Let me just insert here circles, shapes. Let me make 2, 3. I hope my screen is visible to everyone.
Yes, sir.
Okay, so let's say if I am using the draw command, and let's say, see, in general, can we predict about which axis the member will undergo bending? In general, if we have a circular section, is there a way to predict which would be the axis of bending? See, in the case of I section, it would be very pragmatic to say that weaker axis, the buckling tendency is about the weaker axis, right? Or if bending is happening because of some other reasons, then we say that okay, we can make some guess. But in the case of circular section, can we make any guess about what would be the axis of bending? The answer is no. So what we do is that we essentially identify, okay, the bending could be about the horizontal axis or the vertical axis, or a combination, right? We can always split the bending. So if we, for example, we are installing only one strain gauge, let's say here, then will it give us an accurate value? So one strain gauge, can it give us an accurate value?
No, sir.
No, because it may be in the tension region. The strut is under compression, but the strain gauge may show us tension, because we never know. And let's say we are adding one more 2. Will this be reliable?
Again, no.
Why no?
I think it might be, sir.
See, if the bending is about this axis.
No, sir.
If bending is about this axis, then what will happen? Will it eliminate bending?
Yes, sir.
But how about this axis? If the bending is about this axis,
The bending stress would be 0, sir. So it will capture the axial one only.
If, for example, the axis of bending is here, like this. See, theoretically, yes. But what happens is that if there is little bit imperfection in the exact location, then this is not reliable. So that's why the preferred way is that we should have at least 4, so that the bending about both axes, they are captured. They can be eliminated with 4. If we have 4, we would be able to capture the bending also, or we would be able to eliminate bending about both the axes. Alright, if for example it's a biaxial bending, means the axis of bending is neither horizontal nor vertical but something in between resultant axis, then also these will be effective. Okay, but let's say if we are having only 3, will this be okay or not? Let's say we have only 3, but they are uniformly distributed. 3 means we have at 120 degrees. Alright, we have at 120 degrees. So we have here and here, these 3 are there, 1, 2 and 3. And will this be able to eliminate bending? What is your call on this? How much is this angle? This angle is 30 degrees, right? So what is your call? Whether this is suitable or not? Three sensor configuration. Let's say the bending is about this axis. Bending is about this axis. Then what will happen? Will the bending be eliminated or not?
I think no, sir.
No? See, what is the distance from the neutral axis of sensor number 1? It is the radius. And what is the distance of these 2 and 3 from the neutral axis? Because the angle is 30 degrees, it's half the radius. Alright? So, whereas this is under compression, these two will be under tension, but the tensile strain will be half of that in the case of the compression one, if we are assuming everything is in the linear range. Right, and the combined strain from 2 and 3 will be just equal to the one in the compression. Do you agree? If the axis of bending is horizontal, then because on one side we are having 2, other side we are having 1, and because is a circle, so circle is not different, it's very different from any other section. So by the virtue of the circular section, this will be able to compensate, because 2 and 3, these two, the total strain from strain gauges number 2 and 3 will be matching that of strain gauge number 1. Do you agree? So 3 is also fine in eliminating bending. Now in the question we have given you 5. Will 5 be effective or not? Let me use the eraser. Will 5 be effective? What is your guess about 5? So let's try that. Let's say we have the horizontal and the vertical axis. And if we are uniformly distributing 5 sensors, so what will be the angle? How much is the angle?
72.
72 degrees, right? One here, number 1 here,
72.
and number 1 here, 2 here, let's say. So this angle is 72 degrees. and after that we have how much? 18 degrees left. So 18 degrees, and then if you have number 3 here, how much is the angle? 18 is already gone. This is 18. How much is this angle will be? We need 72, so this will be 54. Okay.
54, sir.
And then when this is 54, how much is this left then out of 90? This is 46, right? No, not 46, 36.
36, sir.
36.
36.
So 36 is gone, and then another 36 will make 72, right? So this is number 4. And then we have to have number 5. So number 5 is at how many degrees? This is 18. 18 gone. And 54.
You have taken. So 1 and 2, you have taken 144 degree, right? I guess.
Okay, sorry.
Yes,
Yeah. This is 2. This is 3. This is 4. Now is it okay? Is this how much? How
Yes,
much
sir.
is this now? Check that this is making 72.
54 plus 14 is 70.
18 and 54,
Yes,
right?
sir.
So this would be the configuration of the 5 sensors. Alright. And when you do the analysis, if for example the bending is could be about this axis, you check. When the bending is about horizontal axis or the bending is about the vertical axis, you do a check in terms of whether the bending stresses can be eliminated or not eliminated. Okay, so this is your exercise. You can do this check also, whether in this configuration the bending stresses they are eliminated or not.
So what if we have only 2 sensors? In that case, what will be the issue?
Yeah, 2 sensors, theoretically there is no issue, but what happens is that if they are just little bit here and there, then
Suppose if it is diametrically opposite to each other, in that case, can we say that the result will be same? Because
they
if
are
you see 1 and
exactly
4,
if they are exactly, then bending part will be eliminated. This is one thing. Other thing is the end
So-
effect. At the ends, the stress is non-uniform. Near the ends of the member, the stress is non-uniform. So 2 effects are there. One is the bending effect. Bending effect you may eliminate, but then the other is the non-uniform distribution near the end effect. So that's why the suggestion is that we should have at least 3, and if you have 4, good. Even if you have 5 is also better, because ultimately you are doing the averaging. So at least 3, that is the
Sir?
norm.
Excuse me, sir.
Yeah.
Sir, but how can we do the average of the strain value without taking the absolute strain values? Because my strain diagram will be in negative, suppose in negative for the tension side and in positive for the compression side. So if I'm trying to add positive and negative value, then I don't think it will give me the correct strain values, average strain value.
See, what is
For
the
that,
what is the stress coming? Stress has 2 components. One is the compression part, alright, and the other is the
Yes,
bending
sir.
part, alright.
Yes, sir.
So now what happens is that because of the compression, this would be always in compression. This part will be always compressive, right?
Yes, sir.
This part will be compressive, and this part will be compressive or tensile. This could be both compressive and tensile. So if
Yes, sir.
the bending is not very significant, then the net will be always compressive. But if the bending is very high, then it could be possible that the net is if the member is showing the tendency of buckling, then at some places the net could be tensile. So it may be like this. The distribution of the things could be like this now. You understand? That
Yes,
here we
sir.
have
Sir,
compression, but
in
at
this
some
case
places we have
can.
tension also. So when you are doing the averaging, so that process,
Sir,
it
for that
eliminates
we
the
have
bending.
to add the absolute value. But sir, for that we have to add the absolute value or not?
What do you mean by absolute value?
Sir, I mean, okay, you are saying ki this tension part, if we subtract the tensile strain from the compressive strain, it is going to eliminate the bending.
Yes, finally it is going to be average out. So absolute, what we are doing is we are using the 4L square, sorry, 4 L square, right? For L square, then rho, then the Young's modulus, and then the F2 square minus F1 square. So this is the baseline frequency. So what we are, and let's say we have done the thermal compensation also, so we'll be getting the absolute value. Yes, because we are measuring right from the beginning. When the member was installed without any strain, the strain gauge was installed on the top and we had the measurement of the frequency in the pipe was there, pipe was brought, and pipe was not under any kind of loading. That time we had the frequency, and when now it's under loading, we still have the frequency. So we are getting the absolute strain. Okay. So adding them algebraically, what it will do, it will eliminate the bending. So that's why we do the averaging, that we add algebraically and then divide by the number of sensors, so that eliminates the bending part.
Sir, suppose we have one case, we are having only two sensors, one at the topmost fiber and one at the bottommost fiber. So, suppose that is a pure, not pure. I mean, suppose a load is acting, eccentric load is acting in that case. So, if we are going to average out the strain values, so how we are going to get the load value? I'm still a little bit confused regarding
Let's
this.
say we have, let me go to next page. Theoretically you
Yes,
can
sir.
show it, you can convince yourself. Let me just rub this out. Let me go to the next page and I'll just show you.
So basically, when you add those two, na Himanshu, that axial component will be twice. That's the reason averaging out will be needed.
No, axial component will be twice while adding.
Yes, M by Z component will eliminate each other, but that P by A component will be considered twice.
Yes. So what, Himanshu, I hope you understood. Let's say I have a beam. I'm not just showing you circular. Let's say we have a beam. Okay, we have at the top and the bottom. And same technique we use when we are using the piezo's. We can use the same technique, but let's say we are using here the ESG. Sorry. Let me just draw it correctly. So this is one gauge, this is other gauge, just two. Forget for the timing that we are dealing with only circular section. This is, let's say, the neutral axis. So if for example this is under both tension and bending, tension is there.
Screen is not moving.
Is my screen visible?
Sir,
it's freeze, sir.
It's free, sir.
Okay, let me unshare and share again. Is it visible now? Visible now?
Yes, sir.
Yes, sir.
So I have drawn here this section which is under combined axial force and bending. Okay, so bending is also acting. So we are showing here sagging moment. Okay, so now what will be the net strain here? So the top one, the strain, I'm just putting in terms of the stress, will be P by A and minus M by Z, right, for the top, and for the bottom one, P by A plus M by Z. Sorry, I have to make it T. I have used the symbol, or I can just change the symbol to T to P. All right. Now you just take the average. What will be the average give you? If you just add them, so average will just eliminate the bending part. So average simply P by A. So bending will get eliminated out. Okay. So even for the piezos also we use this concept. For example, if you have asked this question, let me just show you the example of the piezos also. Suppose these are the piezos. Okay, I'm just erasing it some portions. So if they are, for example, piezos, and let's say the member is under combined bending and axial force. So what we do, the top one will be under compression. That means, let's say if the exposed surface is getting positive charge, the bottom, the bonded one will get negative here. And what will happen in the number 2? It will be the other way. So because the bottom one is under tension, so it will be like this. Alright. Now how should we connect them? How should we connect them if we want to eliminate bending? Number 1. How we should connect them if we want only bending? You understood? First is that I am asking you the question. Now this is under dynamic condition, that we want to only obtain the axial modes. If we want to obtain axial modes only, how we should connect them?
Sir, in parallel.
Axial mode, if you want, we must connect them in parallel.
Opposite.
No.
Axial modes
For
means
bending curvature, we are connecting into the series.
yes. So we have to think of this. Let's say if you want only axial mode, then you connect like this. Okay, and what you have done is that the inside of this you have connected to the outside of this, and this we are subjecting them to the sending for the voltage measurement. So this connection, what it will do, if for example there is any bending, that bending will cancel out. It will be like this. Suppose this pure bending, there is no axial force, then what will happen? The cell arrangement will be like this. You are connecting like this now. So the net will be 0 in the case of bending. But if it's axial force, what will happen? If pure axial force, then both will have the same type under axial force. If it's pure axial force, both will have same type because the member is under uniform compression. So outside phase will be, let's say, positive in both. So the axial will get pure axial thing and the bending will get eliminated. Okay. But this is valid only if the section is symmetric. It is bisymmetric or monosymmetric. So axial modes, this connection, and if you want pure bending modes, then how you should connect them? If you want pure bending modes, then you have to connect in a different way. In that case, what you do, you connect the bottom of this with the bottom of this, like this, and send the outer ones for voltage measurement. Then you will get what? You will get pure bending modes. This will eliminate axial forces. Okay, so just convince yourself with this. So we are using this intelligent interconnection method both for strain gauges as well as for the piezos. For example, we have this time we have given a different hammer to everyone, and this hammer is a laboratory made hammer, and which has 4 piezos connected in such a manner that we are only getting the axial forces. The average axial force is we are able to get, and the bending is eliminated out. Okay, any question on this? Okay, now I hope question number 1 is clear to everyone. So now I am sharing question number 2. Okay, question number 2. Question number 2 is that a piezo patch of this size is hanging vertically with a thread. So basically the piezo configuration is like this, that there's a piezo patch like this with a very small thickness, and this is hanging vertically from using a thread, so no restraint. Alright, from a rod it's hanging, and now what we have done is we are applying some excitation. So compute the induced strain under an electric potential difference of 100 volts applied across the thickness of the patch. Means now what we are doing, we are applying an external excitation, means one terminal here, one on the opposite one, and we are applying here potential difference. It could be static or it could be dynamic, so we are applying 100 volts. Okay, so is this equation effect, means converse effect or direct effect? First question is this: is it direct effect or converse effect? See, direct effect is when we are applying stress.
Direct effect.
No, it's converse effect.
Okay. No.
Why it is direct effect? Direct effect is that when we are applying, we have a piezo patch, and when we are applying stress, so because of the stress we have the charges. So how this is direct effect? Direct effect is this, because when we are applying stress, that stress gets converted into the charges, and by the analogy of the parallel plate capacitors, we are generating here some voltage, or the charge is accumulated, and that is leading to the voltage. That is the direct effect. But here in the question we have converse effect, not direct effect. So what is the equation of the converse effect? So converse effect, the strain would be because of the applied stress, which is 0 here, because there is no stress, we are keeping it hanging, free hanging, plus the other component is because of the electric field. The other part is because of the electric field. So it's just like strain under thermal effect. So thermal effect also induces strain, that is called as the thermal strain. So this part is just like the thermal strain. Suppose this was hanging like this and you are increasing its temperature, you are heating it, what will happen? It will undergo expansion, but it's stress free, so it will not have any stress. It will have strain, the thermal strain, but it will not have any stress. So same thing is happening here, that this is undergoing this much of the strain. So what we have asked is compute the strain induced under electric potential difference of 100 volts. So it is a converse effect. So you have to use the equation of the converse effect, not the direct effect. So this is the simple way. D31. And what is electric field? Electric field is potential difference by the thickness. So potential difference is acting across this thickness. So none of you have solved this question correctly. So this would be the answer. Alright, you have understood? So please make sure you understand the direct and the converse effects.
Yes, sir. Yes, sir.
So direct effect equation will not be valid here, because direct effect equation is valid when you are applying some stress. Here there is no stress. You are applying converse effect equation is valid when you are applying some external excitation. Like we had shown you converse effect. You remember the converse effect? We were applying some frequency signal across the piezo and the piezo was vibrating and giving out sound. That is the converse effect. So I hope all the doubts are clear.
Yes, sir.
Alright, so I think we
Yes,
can
sir.
have the attendance now.
Sir, I have one question regarding lab.
Just a minute. Let me see how many are present. Do we need to take attendance or not? Okay, this shows 29 are there, so I think no one is absent. So I think everyone will get the present. Yes, Aniket. Aniket, you are asking question?
Yes, sir. Yes, sir.
Yes, what's your doubt about the lab?
Sir, can I share my screen if you don't mind?
You have question about the lab? Yes, you share.
Mm, 1 minute, sir. Sir, is my screen visible?
No, yes, visible.
Sir, after getting after sir repeating the experiment, if we plot the mode shape, we get the mode shape something like that, and this is also not a correct nature.
Oh, really?
Yeah,
What is the
yes, sir.
frequency
We
you
are
are
also
getting?
getting the same, sir.
Just can you maximize? I want to check. What is the frequency?
Frequency frequency as per your beam data around 43.8 hertz. We are taking between the 40 to 55 or 40 to 60 hertz, and note down the what is the absolute value, what is the real, and what is the imaginary
So
value.
all these values are for one frequency or different frequencies?
Around yes, some frequency lying in 37, some in 40, some in 45, something like that.
No. That will not give you mode shape. Mode shape is by definition the profile of vibration under one frequency.
One particular frequency.
Yes. You have to use only the peak. So your method is fundamentally wrong. You cannot pick frequency as per your convenience.
Okay.
Okay, so do it again and you can personally discuss with me.
Okay, sir.
Alright.
Sir, Costa from this side.
Yes, Costa.
Sir, actually, I have tried to plot the mode shape for like picking each frequencies from 35 to around 55 hertz. So, but still I'm not getting any mode shape in any of these particular frequencies.
Okay. Alright. What you can do is now, instead of using the laborious method, now you use the program which I have just, I will be sharing with you all. So try using the program. Program will, do many things for you. So
okay, sir, I'll just check the programming.
Yes,
because
yes.
I also like minimize it with some frequency input. So once I give that frequency, ith frequency, it will capture all those peaks from each of those FRF. But I will check the same from
you check that.
code which you will see.
Now what I have
Okay, sir.
done in the last day, I gave another hammer. So first hammer because there is a noise component also. So the second hammer I have given to Major Anuj, and he has used that hammer also to obtain the measurement. So you all try, because it's a teamwork. So let's say, because the hammer tip, it should generate those frequencies. So we are not using shaker here. Shaker here, if we had used shaker, we would have just excited the beam at around from say 35 to 50, so that peak is captured. But when we are using hammer, it may be possible that some of the frequencies they are not excited. So that's why we have given another hammer. So every group, you try your best to get the mode shape. Either you use manually, or you use now the program of the program which I will be just sharing. But be patient with the mode shape acquisition. It's not like a very quick thing. So please be patient with this. So finally, what we'll be using a very sophisticated software. Once you understand the basics, that how it works, that was the objective. So in the subsequent labs, we'll demonstrate you using M+P software. So M+P software, you can even get, the software helps, and you can get even very difficult mode shapes also. You can very easily get using that M+P software. So we'll demonstrate you that also. But why we have given you first laborious process, so that you at least learn right from the basics how it works, and it will be very concretely understood. Okay.
Sir, I just have one more question here. Sir, when we have taken the data with the like second hammer, which you are referring, so we have kept the time interval as 0.4 milliseconds. So will that impact anything, or like
no, it doesn't matter. See,
okay, sir.
Our frequency, what is our target frequency? Our target frequency is 30 hertz, right? So 30 hertz.
Yes, sir.
So if we want to capture a frequency of 30 hertz, so 30 hertz means in 1 divided by 30 seconds is how much? Can anyone do? 1 divided by 30 is how much? Something right, 0.003 or 0.03?
33 millisecond. Millisecond.
0.033, sir. Sir, 0.33.
0.033 seconds. So in 0.033 seconds, we are getting one wave. One up and then one down. If we want to capture that correctly, within 0.033, we should have at least 5 to 10 measurements. Then only we'll be able to capture completely the crest as well as trough, right? So our measurement frequency should be 10 times of that. So for example, we are targeting frequency of how much? 33 or 30 hertz. So our sampling frequency should be say 10 times of that. That is 300 hertz. So in present case, we are using 1000 hertz. We are basically using our sampling frequency is 1000. So we are sufficiently well equipped with our measurement. All right. So if we are reducing the sampling interval to 0.4 millisecond instead of 1 millisecond, that means we are further helping us further.
More.
Yeah, that will
more
be
defined data kind of
but
thing we have
even 1 millisecond is more than enough. 1 millisecond is more than enough. If you are making 0.5 millisecond, that's another thing, but it will not change the results drastically, because we have already reached our discretization from the point of view of time is good enough. Okay, so it's just like the finite element. You can use 10 elements to represent beam, or you can use 100, or you can use 1000. After certain number of divisions, it will not make it, convergence will be happening, and it will not make much difference. All right.
Okay, sir.
All right then. So I think we close. But you play with this data, play with the program I have given, and that will be learning. So okay, so we finish,
Okay, sir.
and the next two will be in the form of the tablet pen and notes. Okay.
Okay, sir.
Good night to everyone.
Good night, sir.
Thank you, sir.
Good night, sir.